Hi ladies and gentlemen, in the last two videos we have seen the application of flip-flops. We saw the application of T flip-flops in ripple counters and JK flip-flops in the case of synchronous counters. Now we see the application of shift register, especially the application of flip-flops, the D flip-flop in registers and shift registers. So registers are used to store one bits of information in that. So it is a cascade of D flip-flops. So in a register, if the data can be shifted from one end to the end, that is called a shift register. So let us start with that presentation. So the speech is organized in your learning outcomes, then theory and design of shift registers, then a shift register configured as a ring counter, and a shift register configured as a twisted ring counter or a Johnson counter. Then we will see the demonstrations in QUCS, and then we will see a universal shift register in QUCS, and then we will understand an IC 7495, that's a universal shift register, then the summary of understanding. So you will learn the operation of a 4-bit shift register using D flip-flops, and you will observe 4 kinds of operations. That is a serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. This means that suppose I have a 4-bit shift register that is composed of 4 D flip-flops. Always D flip-flops are used for making registers. Likewise, T flip-flops are used for ripple counters. Here D flip-flops, because D flip-flop is used for storing a bit. If a 0 is input at D, it will appear at the output. If a 1 is put, that 1 will appear at the output. So it is used for storing data. So if data input is a serial operation and the output is a serial operation, that is one possible way. Or else I can put the data in serially and you can take it out parallel. And you can parallelly load data and you can take it out serially, or you can load the data in parallel and you can take it out in parallel. Okay, so there are 4 possibilities. So you will understand these 4 data transfer operations and you will implement this in QUCS. Then you will learn to realize the ring and Johnson counter using QUCS. Okay, how to convert a shift register into a ring counter or a twisted ring counter or a Johnson counter. Then you will learn the operation of a universal shift register. You will see the demonstration in QUCS, and then you will familiarize a universal shift register IC called 7495. So these are your learning outcomes from this session. So a register is a synchronous digital circuit for data storage. So the data is fed to a register and it is kept there. It can be serially or parallelly read out. So all flip-flops are clocked simultaneously. That's a synchronous counter. It is composed of D flip-flop with each flip-flop storing 1 bit at a time. A shift register is a register in which the data can be shifted in either direction with the application of clock. Okay, a register is used for storing the data, and a shift register is used for not only for storing but for shifting the data from one end to the end. You know the importance of shifting. That is a lift shift by one unit, one bit is equivalent to a multiplication by 2, and a right shift by 1 unit is a division by 2. Suppose I have a bit 1, if it is shifted to the left it becomes a 1 0, it is a 2. If it is shifted again to the left it becomes 1 0 0, that is 4, that is another multiplication by 2. So that is the importance of shifting. So often this is used in processors, like you have the accumulator in any processor, a DSP processor or a microprocessor. You can see that is a shift register because data can be shifted in either direction. So the circuit you can see in this, this is a circuit of a 4-bit shift register. Here I use 4 D flip-flops. You can use JK flip-flops, but you have to configure it as a D. In that case you have to, here if it is a J and K input, you have to connect an inverter between J and K, and here Q should be connected to J and Q bar should be connected to K. That will make the second, third flip-flops, etc. D flip-flops. Anyway, you usually D flip-flops. Even if you see circuit diagrams involving JK flip-flops, you can see that they are configured as D flip-flops. Now this is your serial input. Here you can see that all the 4 flip-flops are clocked in parallel with a common clock. This is a synchronous circuit, and there is a common clear signal. This is for clearing all flip-flops. and a preset is connected here. Here you can see that the parallel in operation, you can see the serial data is coming through the first D flip-flop. Okay, so if I apply a 1 here, and if the clock is there, then this 1 will appear at Q. Now if I assume that I have initially cleared all flip-flops, say suppose it starts with a 0 0 0 0, and if I apply a serial bit, say 1 here, at the next clock this becomes a 1, this becomes a 0 0 0. Okay, so this Q is connected to a nested D. So if you give one more clock, this 1 will appear here, it will be 0. If I apply one more 1 here, it will become a 1 1 0 0, that way. Anyway, I will show you the simulations. Now this is how I do the serial in, serial out. You feed the data here and you take the data out in serial. That is applying clock signal. So if I apply 4 clocks, the flip-flop will be loaded with the data, and if you apply 3 more clocks, then the data will be sent out of the serial output pin. So serial in parallel out is possible. You can have parallel connection from here, Q0, Q1, Q2, Q3. You can feed the data in serially and you can take it out parallel. There is nothing very exciting about that. It is very pretty straightforward. Now how do you apply parallel data? Here in this circuit I use the preset input. So preset is an asynchronous input. So what I can do is I have a preset enabled signal here. If this preset enabled signal is a 0, then all these NAND gate outputs are high, so the preset is disabled. Now if I make this preset enable a 1, then that means the parallel data is enabled. Okay, so now this serial data or shifting operation does not have any role, because you know that preset is an asynchronous input. So whatever data input or clock is there, it doesn't matter. Whatever is activated as a preset, so that will take the predominance. So what will happen is, if I make this preset enable a 1 and these bits are active, say suppose I give a 1 0 1 0 at say P0 is 1, P1 is 0, P2 is 1, and P3 equal to 0, what will happen is this is a 1, so it becomes, this output becomes a 0, this is a 1, this is a 0, this is a 1, because this P0 and P2 are 1s. So these are NAND gates, so when both the inputs are 1, the output becomes a 0. So this preset input becomes a 0, this preset input remain high, this becomes, because this is a 0, I assume that is a 1 0 1 0. So here this P2, this gate output will be a 0, this gate output will be a 1. So what will happen is this preset, this will be preset 1, this will remain at 0, this is preset 1, and this remains at 0. So the flip-flop, the register is loaded with 1 0 1 0. So you can give a suitable pattern and you can load that data into this register. Now you can take out that data like this. You can apply data here at P0, P1, P2, P3 and take the data out in parallel, Q0, Q1, Q2, Q3. That is a parallel in serial out operation. That's a, sorry, parallel in parallel out operation. I'm sorry. That is a parallel in parallel out operation. You feed the data through these presets and you take the data out through the Q outputs. That is a parallel in parallel out operation. You can have a parallel in serial out operation. That is when you give these data in parallel through these presets, then what you can do is you can take it out of this serial out. What you have to do is you apply some clock pulses. When you apply one clock, this will shift to the right. When you apply the next clock, one more shift, and after 3 clock pulses, all your bits will be out of this serial output. Okay, so this is how you do the 4 data transfer operation: serial in, serial out. That is, the input is through the serial pin and the output is through the serial out. You apply clock pulses and you see the shifting of the data through this D flip-flops, and the out goes your data values. Serial in parallel out means you apply 4 clock pulses and feed the data, and here out of this Q0, Q1, Q2, Q3 you take the data out. Okay. On parallel in operation, that is through these preset terminals. So you have a preset enable. If the preset enable is made 1, the preset is enabled, so pins are enabled. So apply a suitable pattern here, and that will reflect the output of these flip-flops, output of this register. That either you can take it out parallel, like you feed the data through P0, P1, P2, P3, and you take the data from Q0, Q1, Q2, Q3. So that is a parallel in, parallel out operation. You can feed the data in parallel through P0 to P3, and you can take the data out of a serial output by applying clocks. That's a parallel in, serial out operation. So let us see this simulation in QUCS. You can see that this is my circuit. Here I have applied this, make it a bit bigger. Yeah, you can see that here is my, these are my 4D flip-flop that is connected to a parallel clock. Okay, synchronous circuit. So here there is an initial reset. This resets all flip-flops to 0000, and I have given suitable signals also. Here I have a clock of say 1 nanosecond, 1 nanosecond, and here I have a preset that is initially low for 1 nanosecond and remains high for the rest of the time. So it's an initial reset. So here I have given some inputs, like some serial input that is high for 3 nanosecond and low for 20 nanosecond. So it's a short high, it's a 1 applied at the input of the data input line, so it will be shifted through the register. Now here you have this thing, this is now disabled. Or do I have a better circuit? No, we will proceed with the circuit. Now, what you can see is, first we will, this terminal is now disabled because the preset enable is now disabled. So this parallel inputs have no role here. Only this data input is given, and serial in parallel out and serial in serial out operations you can see. Now I will run this simulation, and you can see that this is my data input. This is initially, these are my clocks. Every 1 nanosecond this clock comes. Then there is an active low reset here. This makes all data output. This is Q0, Q1, Q2. This is data output. This is Q3, because all outputs are now cleared. Q0, Q1, Q2, Q3. They are all cleared due to this reset. So initially all flip-flops are at 0000. Now what happens is, then now there is an active clock here. This is an active low clock. So what happens is, initially the data input becomes a high. It remains for high for 3 nanosecond, and the rest of the time it is a 0. So this 1 will shift through this register when you apply the clocks. Here there is an active clock here. So this data input appears at the output of Q0. This Q0 will appear at Q1 at the next clock. You can see the clock here. At the next clock at 4 nanosecond, this Q0 will appear at Q1. This is the D input of Q1, the second flip-flop. Now this output will remain, get at Q2 at 6 nanosecond. And this data ultimately reaches the data output at this point, that is at 8 nanoseconds. Now you can see that the data shifts through this register from left to right. Now I can have a parallel feeding. If I make this a 1, if I make components, and I'll make digital components. Can make to logic 1. Okay. Now this 1010 pattern will get at the output. Now you can see that the data, I will remove this data input. I'll place a 0 here. I am disabling this now. Now you can see that this parallel input appears at the output. You can see that it is you can see that it is what I have given is a 0101 pattern. Okay, 0101 pattern. So initially, after clearing, here the flip-flops are cleared, and now the output becomes a data output, because I fed the data through the preset. It's a QUCS process, so it becomes a 0101. You can see that this data 0101 is loaded into my register 0101. Now you can see that this either you can take it out in parallel, okay, through Q0, Q1, Q2, Q3, or you can shift through this. You can see the shifting of the data. Initially this data in has no meaning. Now it is Q0 is high here. At the next clock you can see that it appears at Q1. Now you can see that this Q2, this high appears at the output at 4 nanosecond. You can see this shifting operation. So you have observed the parallel in, parallel out operation and the parallel in, serial out operation. Now let me go back to my presentation. So this is how the circuit works. Now ring counter means if the output of the last flip-flop, this serial output, if it is connected to the input, back to the input, then it becomes a ring counter. It is a feedback circuit. It's the feedback at the output that makes it work like a ring counter. Like suppose I start with a 1000, then after one shift this 0 will appear here, so that the next count will be 0101, the next count will be 0010, next will be 0001, and the last will be 1001, that way. Okay, that's a primitive counter. Nobody uses this kind of counters. People use ripple counters or synchronous counters, but this is a primitive kind of ring counter. So I will show you the simulation in QUCS. You can see this operation. You can see that the Q output is fed back to the D input. Okay, Q output is fed back to the D input. So you can see this thing. Then what I do is I have to load this with some data. Okay, I have to load it with some data because the serial input is no longer there. Or you can overreturn give, but what I do is I give this data input and take it out and connect to the D input. Now I have played the data in parallel. Suppose I have a 1001. Suppose I load this data with 1000. Okay, through these presets. Now then let us observe the shifting and the ring counter operation. Now I will simulate this circuit. Now you can see that here an initial reset is there where all flip-flops are reset, and then what I do is I apply this parallel input so that it becomes a this becomes the pattern 1000. Okay, now what happens is this data output that is fed back to the input. So at the next clock what happens is Q0 becomes a 1, others are 0, it is a 1000. At the next clock what happens is this 1 appears at the second thing, it becomes a 0100. At the next clock it becomes 0010. Then at the next clock it becomes 0001. This is my original thing. It starts recounting. So you can see this, you can observe here. Initially all flip-flops are reset. Then the clock at the next clock I preset it to 0001. At the next clock it becomes a 1000. Then at the next clock it becomes a 0100. At the next clock it becomes a 0010. At the next clock it becomes a 0001. Again it goes back to my original account, that is 1000. Okay. Now you can see that with a 4 element register or a 4-bit register, the maximum number of count cycles you can have is 4 only. Okay. If I have an n-bit ring counter, I can count only n clock cycles. This is a very disadvantageous counter. You can know that with n flip-flops with a ripple counter or synchronous counter, you can have 2 raised to n. You can count 2 raised to n clock cycles. So this is an inefficient counter. But it's an application of the shift register. Now what you can do is, there is another kind of ring counter, that is a twisted ring counter, or something called a Johnson counter, wherein instead of feeding the Q output, you feed the Q bar output. Okay, the complemented output of the last stage, that is a last stage Q bar, that is connected, fed back to the serial input of the first stage. So here the specialty is that you can count the 2 n clock cycle. So I will show you the simulation in QUCS. Here you can see that instead of connecting Q output, you connect the Q bar output of the last stage to the input. Then as usual, I feed it with the 1000, some arbitrary pattern. I applied this in parallel through the preset inputs, okay, parallel inputs. So we will see this parallel in serial out operation. We will see the operation of this twisted ring counter. So with the 4 flip-flops, it will count 8 clock cycles. Still, it is a very inefficient counter. So you can see these waveforms here. Here you can initially it starts with 000, everything is reset. Then we load with 0001. Then it starts counting this way. If you observe this, instead of the waveforms, if you observe this table, you can very easily understand this. Initially, I loaded this register with 0001. Here clock has no effect because the preset is active here. You can see that the first count is 0001. Then this is the Q output of the last stage. So Q bar is fed back to the input. So here the Q3 output is a data output. That pin is a 1. So the 0 is fed back to the input. So the next count becomes a 0000. Now the last bit is a 0. So its complement 1 is fed back to the input. So the next count becomes 1000. Okay, here also the output is a 0. So 1 is fed back to the input. So the next count is a 1100. The next count is a 1110. The next count is a 1111. You can see that the last bit is a 1. Its complement is fed back to the input. So the next count becomes a 0111. Next is 0011. Next is 0001. Next becomes a 0000. So next will be 1000. Okay. So you can see that with the 4 flip-flops, you can count 8 clock cycles. Okay. With a ring counter, ordinary ring counter, wherein you feed back a Q, you can count 4 clock cycles. Here with the Q bar fed back to the input, you can count 8 clock cycles. Still, it's a very inefficient counter because with the ripple counters, you can count 2 raised to n clock cycles. But this is an application of the shift register, because such feedback connections are very useful in making pattern generators, sequence generators, etc. So this is one such simple application. Then we will see a universal shift register. A universal shift register, what it does is it supports all 4 data transfer operations like the parallel in, parallel out, parallel in, serial out, serial in, serial out, and serial in, parallel out. In addition to that, it has to perform left shifting and right shifting. So far you have seen the right shifting of the bits. It is possible to shift them to the left also. So all these 4 data operation plus left shifting and right shifting together, that forms something called a universal shift register. So I will show you a simulation in QUCS. I will show you the circuit as well as the simulation in QUCS. Now you can see this circuit. This QUCS subcircuit of a 4-bit universal shift register. Now all the 4 data operations plus left shifting and right shifting is possible in this circuit. So how this is made possible is with the help of a 2:1 multiplexer. Like you can see the D flip-flop, the 4 D flip-flops are there. They are connected to a common clock. And this common clock, there is some speciality. The clock also, 2 clocks are there. One is the right shifting clock. This is a clock R. This clock is for right shifting the data, and this is for left shifting the clock. So this right shifting or left shifting, that is decided by the mode of operation. If the mode is a 0, what will happen is this 0 comes here, okay, and this one. This AND gate is disabled, so this is the AND gate for clock left shifting. So mode 0 is for right shifting. When mode equal to 0, this point becomes a high, and this AND gate is enabled. So this right shifting clock is enabled, and this right shifting clock passes through this OR gate and appears at the clock terminals. Okay, so here it's a 2:1 multiplexer. This is a 2:1 multiplexer. What it multiplexes is right shifting and the left shifting clocks based on the mode. Okay, so if the mode is 0, this lower AND is disabled, but this upper AND is enabled. The upper AND passes the clock right clock through this AND gate and this OR gate into the parallel clock signal. Okay, so if the mode is a 1, this AND gate is lower AND gate is enabled and it passes the clock left. This upper AND gate, this top AND gate, that is disabled. So this clock left signal appears here. This is an OR gate, it appears at all the clocks. So this mode equal to 0, that is for right shifting, and mode equal to 1 for left shifting. Okay, and again you can see that you have to see how the inputs are fed up. Now here you can see that both the parallel inputs and serial inputs appear at the D input and not through the preset terminal. Here this circuit is designed such a way that both the serial input as well as the parallel input, they appear at the D input of the flip-flop and not at the, earlier in the other circuit I showed the parallel input appearing at the preset terminals. Here it is not like that. So here this mode decides which operation is there, whether it is a serial operation or a parallel operation. If the mode equal to 0, what will happen is this line will be a low, because there are two inverters, so this mode equal to 0 will make this line a low. So what will happen is the right set of AND gates here in this 2:1 multiplexer, they are all disabled. Okay, so what are they connected to? They are connected to the parallel bits. So those parallel inputs are now disabled. When I make mode equal to 0, when mode equal to 0, what is it? It is taking the right shifting clock. Mode equal to 0 means it is taking in the right shifting clock. But at that time, the parallel input operations are disabled. When mode equal to 0, this line is a low. And these right AND gates here, this AND gate, this AND gate, this AND gate, they are all disabled because this bit is a 0. This common bit is a 0. But the left AND gates are enabled because this is a 0, this is a 1. So this point is this left AND gates in this 2:1 multiplexer, they are enabled. So how they are, now what is it receiving? When they are enabled, what happens is the serial data can pass through this and through this OR gate and reach this D output. Now this Q output of the first gate that is connected to the Q in the multiplexer here, this AND is now enabled. So this Q output of the first D flip-flop that travels through this and at the D input of the next stage. Then Q output of that stage passes through here, and this left AND gate that is enabled now, this 2:1 max, and through this AND or it reaches this D. And this Q output is connected to the next D through this 2:1 multiplexer. You can now have the serial input, you can apply the serial data here and observe the parallel output here through this parallel ports, output ports. Or you can observe through right shifting clock, because the mode equal to 0, when mode equal to 0, what happens is this right shifting clock is enabled and you can observe the right shifting with that. If you want to do left shifting, what you have to do is you have to change this mode to but before going to that, let us see the parallel operation. So when for parallel operation, what you have to make this mode a 1. Okay. Now when you make this mode a 1, your left shifting clock is enabled. There is a reason for that. Now this left shifting clock is active here, but what happens is when this mode is 1, this line is now active. This top line is now active. So what happens is the right AND gates are now enabled and the left AND gates are disabled, because this when mode is equal to a 0, this becomes a low, and this left AND gates are now disabled. Now what happens is, since the right AND gates are enabled, what will happen, this parallel input I apply at A, B, C, D, those inputs are applied to the D inputs, and this output you get at Q outputs, which I can take out parallel through this P2, P4, P6 and P8 ports. Okay. Now when this mode is a 1, this line is active and parallel inputs are now activated. This left AND gates are now disabled. Okay, this parallel input, they appear at the D input of the thing, and now I have my left clock. So once a clock is there, these outputs will be available at the parallel ports. Now you can have left shifting operation. How I do that? I have to do an external connection. Now my clock left clock is now enabled because mode is 1 and the left clock is now enabled. The scenery is for a left shifting operation, but for doing that what I have to do is instead of this parallel data, what I have to do is this P8 should be connected to the parallel input here. This output should be connected to this P8 should be connected to the input parallel input of the proceeding stage, and this output proceeding stage output, this should be connected to the parallel input of the stage before that, that is this, and this connection should be, this output should be connected to the input of my previous stage. So this I have to connect externally. So we will see these all these operations with the help of this sub-circuit. So I will see one by one. Let us see this unit shift operation. So here I use this thing. I use this universal shift register, this sub-circuit. So if you go into this sub-circuit, you can see the same circuit there. Okay. So I am working with the same circuit. Now I can see the operation. This is just a right shifting operation. You can see this operation here. You can see that this serially. What I do here is I apply these clocks, and I observe this output. Okay, we will see something better. We will see universal shift register parallel in serial out. Okay, this is a parallel in serial out operation. Here you can see that I have given the inputs in parallel. Some pattern is given here. This is serial input line. These are the parallel input kind of pattern like a 0 1 0 1 is given here. Now you can see this simulation. You can see that initially, so I have some parallel data coming in, like it's a 1 0 1 0. Okay, the mode is up to this point mode is a high, meaning that is a parallel operation. Here mode is a low, so you can see the serial shifting from here to here. You can see that this data is getting shifted to the right. Up to this point this mode is a 1. Okay, up to 10 nanosecond the mode is a 1, so that is a parallel operation. So here I load the data in parallel. The data is 1 0 1 0. Now you can see that here the mode becomes a 0, so right shifting happens. So you can see that this data at here, this QA, this comes at QC, and this data at QC, this comes at QD. You can see the shifting of the data from here to here. There's a 1 here, there's a 1 here, there's a 1 here. So with 3 clock cycles, you can see that the one at the input that reaches the output. So this is how I do that. Now I can have more such connections. This is a serial in serial out operation. So here I give the serial in data here. One is fed here. Parallel in is disabled. So you can see this simulation. You can see this operation. Okay. Here you can see that the mode is 0 here, and here you can see that the data shifts to the right. Initially the serial in is kept at 1, and QA becomes a 1 here. Then at the next clock cycle QB becomes a 1, then QC becomes a 1, then QD becomes a 1. You can see that after 4 clock cycles the data at the serial input that appears at the data output or serial output. You can have a ring counter with that, like you can use it as a ring counter. Here you can see that the QD output, this is fed back to the serial input. This is my serial input, and 9th port is my serial input. This QD output is fed back to my input. You can see the what do you call the ring counter operation. Here you can see that the mode is 1 and here the mode is 0, that is for right shifting operation. I initially start with a 1 0 0 0, next count is a 0 1 0 0, next count is a 0 0 1 0, then it is a 0 0 0 1, then again it becomes a 0 0, it again becomes a 1 0 0 0. Okay, you can see that there are 4 clock cycles that are being counted. Now you can see the twisted ring counter. Yeah, you can have a ring counter here. This is a twisted ring counter. Here what I do is the QD output that is inverted and it is connected to the serial input. So this is a twisted ring counter or a Johnson counter. So you can make this circuit at home and you can simulate all these things. Here you can view this simulation. I don't go into these waveforms, you can see very clearly. Here this table is better. Here it is initially I reset all flip-flops to 0 0 0 0, then I parallel load a 1 0 0 0, next is a 1 1 0 0, because this 0 at the QD terminal, that is inverted and fed back to the input, so at the input it becomes a 1 1 1 0 0, then the next clock cycle is 1 1 1 0, next is 1 1 1 1, then I have if the last bit here is a 1, so its complement is connected to the input, so it becomes a 0 0 1 1 1, then it becomes a 0 0 1 1, then it's a 0 0 0 1. Okay, now the last 0 is fed back to the input, making it a 0 0 0 0. Now you can see that it counts 8 clock cycles, 2 n clock cycles. So n is 4 here. I have a 4-bit stage and I have n clocks. It counts 8 clock cycles. Now there is a left shifting operation. Now left shifting, right shifting, there is nothing new. You have seen that left shifting means I have to connect this QD output. You can see that this QD output is fed back to the parallel input of the flip-flop before that, and QC output, this is connected to the parallel input of the stage before that, that is a B flip-flop, and this QB thing that is connected here and connected to the input of the first flip-flop. Now then I have to make the mode equal to 1 and I have to have the common clock. This clock is given in common, but that left shifting and right shifting clocks. So you can see the simulation here. You can see that initially I start with a 0 0 0 1. Now this 1 is shifted to the left. At the next clock cycle it becomes a 0 0 1 0. At the next clock cycle it becomes a 0 1 0 0. At the next clock cycle it becomes a 1 0 0 0. Then it becomes a 0 0 0 0. Okay, you can see the 4 clock cycles in which the bit 1 is shifted from right to the left. Okay, so this is how you realize a universal shift register. You can go to the circuit, you can go inside this sub circuit. This is actually a realization of the 7495 shift register, internal circuit of a 7495 shift register. So that we will see. So you can realize this circuit and you can make it into a sub circuit, and you can use that sub circuit in other circuits. You can take it out and connect these required ports and make it a right shifting stage or a left shifting stage or a ring counter or Johnson counter or whatever you like. So let me go back to my presentation. Now, one such universal shift register in IC form, that is called a 7495. It's a popular 4-bit shift register that features right shifting, left shifting, parallel and serial operations. And that pin diagram is in this figure. You can see that this is a serial input. The first bit is the first pin is a serial input, and this A, B, C, D are the parallel inputs. Okay. Then there is a mode pin. You can take it 1 or 0 and use accordingly. 7th pin is a ground. 14th pin is VCC, and these are parallel outputs QA, QB, QC, QD, that is pins 13, 12, 11 and 10. Then these are the 2 clocks, the parallel and serial, the right shifting and left shifting clocks. So probably you are most likely we short these things and apply a clock. Now you can see the serial in the wiring diagram for serial in and right shifting operation. You can connect the serial data input here and keep this ABC open, ABCD open, because I am not using the parallel input. This mode is kept at logic 0 so that right shifting is possible or serial operation is possible. Then you can connect this ground and VCC and connect for normally on LEDs like Q4, QA, QB, QC, QD. Okay, so when these outputs go low, these LEDs will glow. Then you short these two clock inputs and apply the clock here. Apply some data here like F1, keep it at F1, and you can observe this data going through this QA, QB, QC, QD. Okay, you can observe the serial in and serial out operation or serial in parallel out operation. This QD output is your parallel serial output. This QA, QB, QC, QD, they are my parallel outputs. QD output is a serial output. Now you can see that this another operation wherein you connect these things. This is for right shifting. You can see that this C is connected to this QD. You can see that this QD is connected to C. So this is for left shifting operation. This QC is, this caption is not very correct. This QD, what is my QD? This is my QD. This is connected to C input, and this QC is connected to my B input, and QA is connected, QB is connected to my A input. This is for left shifting operation. So when you come to the lab, you can go to the technician and ask for a 7495 IC and these components, and you can connect it on the breadboard. Okay. So for parallel loading, what I have to do is you keep this way. This serial input is unused, but at this ABCD inputs you feed some data like a 1001 or 1010 or any pattern of your, any 4-bit pattern of your liking. But keep this at logic 1. This is for parallel operation. Here you see that it is at logic 0. Okay, this is for shifting. Okay, this is for left shifting, and this is for parallel loading. You can apply clocks here and observe parallel in, parallel out operation, and you can apply the clocks and observe parallel in, serial out operation. Okay, so by a simple 7495 IC you can demonstrate the use of a universal shift register. Now coming to the end, the summary of understanding. Here in this video you understood the operation of shift register and the 4 data transfer operations. That is a parallel in, parallel out, parallel in, serial out, serial in, serial out, and the serial in, parallel out. Then you learn the implementation of a 4-bit shift register in QUCS. Then you learn the implementation of a 4-bit universal shift register in QUCS. You understood all operations, the left shifting, right shifting, and the 4 data transfer operations. Then you familiarize the operation of a 7495 universal shift register IC. And that is the end of this presentation. I thank you all.